Hi, my name is Arash Mirzaei. I'm a researcher at Faculty of Information Technology of Monash University. I'm going to present you my joint work with Amin, Jiangshan, and Ron. Our joint work is a fair and privacy-preserving watchtower scheme for Bitcoin, which is called FPPW. Firstly, I briefly introduced the concepts of payment channel and watchtower. Then some of the properties of a watchtower scheme will be formally defined, and those properties are fairness, privacy, and coverage. And we'll see that none of the existing watchtower schemes on Bitcoin can achieve both fairness and privacy. Then an overview of our scheme FPPW will provide it, and we'll see that FPPW can be deployed on Bitcoin and can achieve both fairness and privacy. Scalability of blockchains is an open grant problem which limits adoption of blockchain-based technologies. For example, Bitcoin can process up to 6 or 7 transactions per second, which is much lower than the figures for centralized payment systems such as Visa. This limitation has led to many solutions. One of the promising solutions is called payment channel, and this work targets this category of solutions. But what is a payment channel and how does it work? A payment channel allows two channel parties to fund a 2 multi-sig address on the blockchain, and using this funding transaction, they open their channel between themselves, and after that they can perform several transactions off the blockchain, and finally each user can record the latest state of the channel on the blockchain, and by doing so close the channel. However, it's possible actually that a dishonest channel party, let's say Alice, publish an old state on the blockchain in order to maximize her profit. So there must be a way for her counterparty, Bob, to prevent Alice from doing so. Some of the important payments channels, such as Lightning Network for Bitcoin or Raiden Network for Ethereum, are based on these assumptions that parties remain always online in order to monitor the blockchain and detect misbehaviors from their counterparties and react to those misbehaviors. Since for ordinary users this requirement could be difficult to achieve, channel parties might delegate this task of monitoring and reacting to a third party called Watchtower. But how does a Watchtower work? Assume that Alice and Bob has a payment channel between themselves, and this payment channel is in state 5. So Alice and Bob are not supposed to broadcast states 1 to state 4 on the blockchain. Now suppose that Bob wants to go offline for a while. Before going offline, he hires a watchtower, gives the revoked state as well as some evidence to the watchtower, and the watchtower is supposed to monitor the blockchain network, looking for one of these revoked states on the blockchain. Now assume that Alice is dishonest and broadcasts a revoked state on the blockchain. The watchtower finds a match between one of the transactions which has been broadcast on the blockchain and one of the stored states in its database, and once the match is found, the corresponding evidence is published on the blockchain. In other words, the watchtower doesn't allow Alice to finalize the channel state using an old state, and by broadcasting this evidence, actually Alice loses all her funds in the channel, and Bob, for example, in Lightning Network, Alice loses all her funds in the channel, and Bob takes all the channel funds. I just wanted to give you a rough idea on how Watchtower works, there are several Watchtower schemes in the literature, each focusing on different properties. In the next few slides, I wanna introduce some of the properties of a Watchtower scheme. Let's start with Watchtower fairness. In some schemes such as Monitor and DCWC, the Watchtower is rewarded upon fraud, meaning that if the channel parties act honestly, they don't commit any fraud, and the Watchtower is not rewarded at all, which is why we call such schemes unfair with respect to the Watchtower, because anyway, Watchtower has spent some resources in order to remain online and watch the channel for the hiring party. So a payment channel with Watchtower scheme is called fair with respect to the Watchtower if firstly the honest Watchtower is rewarded with some non-zero amounts of coins, and secondly, given that the honest Watchtower has logged some collateral as part of its watching service, he must be able to redeem all his collateral once the watching contract terminates. I define channel party fairness with two extreme cases. In the first case, assume that there's a payment channel between Alice and Bob, and the payment channel is in state 5, and in this state, Bob has 6 coins. Also, there was a state 3, in which Bob didn't have any coins. Assume that Alice broadcast on state 3 on the blockchain, and since the Watchtower is non-responsive, the channel gets finalized using this state. It means that Bob loses 6 coins in the channel. In some schemes such as Monitor and DCWC, or as well as Outpost, the Watchtower doesn't compensate the hiring party's loss, meaning that although Bob lost 6 coins, the Watchtower doesn't compensate this loss for Bob, which is why we call such schemes zero party fair, or we say that such schemes provide channel party zero fairness. Another extreme case is if the Watchtower compensate 6 coins of the loss of the Bob. For example, meaning that all the Bob's loss is compensated by Bob. Such schemes are called one party fair, or we say that such schemes provide channel party one fairness. For example, for Cerberus, it's a Watchtower scheme. The Watchtower locks some collateral as part of the watching contract, and the value of the collateral equals the channel capacity, and if the Watchtower is non-responsive, all the collateral is given to the hiring party, so Bob can be sure that he doesn't lose any funds in the channel. To cover the cases in between, we parameterize our definition using a parameter called alpha. Assume that in our scenario, Bob loses 6 coins in his channel with Alice, but since this Watchtower scheme provides channel party alpha fairness, Bob can be sure that alpha times 6 coins of his loss is compensated by the Watchtower. So we say that such Watchtowers provide channel party alpha fairness. Coverage is another relevant property to provide fairness with respect to the channel party. The Watchtower must lock some fund, some collateral to be given to the hiring party if the Watchtower is non-responsive. But we know that the higher collateral, the lower liquidity and the lower maximum capacity of channels that can be covered by the Watchtower. Coverage actually parameterize these factors. Assume that we have a payment channel with capacity of X coins. If to monitor this payment channel for both channel parties, the Watchtower requires to lock C coins as collateral. We say that this scheme provides beta coverage, with beta being X over C plus X. For instance, for some schemes such as Monitor and DCWC, the Watchtower isn't required to lock any collateral, which means that C equals 0 and beta is 1. On the other hand, for some schemes such as Cerberus, the Watchtower is required to lock some collateral. The amount of collateral for Cerberus, for example, is twice the channel capacity if the Watchtower is gonna be hired by both channel parties, which means that C equals 2 times X and beta is 1/3. Let's continue with privacy. Assume that we have two payment channels, one between the honest channel parties A and B, and one between the honest channel parties A prime and B prime. Both channels have the same channel capacity of X coins and the same number of channel updates. We know that the first and the last state of the channels are broadcast on chain, so it's possible for anyone to knows how channel capacity is distributed among the channel parties in those two states. But what about states 2 to n-1? Assume that according to a random bit B, one of these two sets of data is selected and is given to a probabilistic polynomial time adversary, and adversary is gonna guess whether the data belongs to the first channel or the second channel, and she wins the game if her guess is correct. In other words, she wins if B equals B prime. We say that this payment channel provides privacy if the probability of winning the game minus 0.5 is negligible. For instance, in Cerberus, all the commit transactions must be given to the Watchtower. So it is possible for an adversary, let's say Watchtower, to learn how channel funds are redistributed among the channel parties from one state to the next, which is why we say that Cerberus, failed to achieve privacy. But there are, some schemes such as Monitor and Outpost, for example, in which it's not possible for a third party other than the channel parties to learn anything regarding this redistribution of funds among the channel parties from state 2 to n-1. So we saw that some schemes such as Monitor and DCWC fail to provide fairness with respect to the Watchtower. These two schemes, as well as Outpost, cannot provide fairness with respect to the hiring party. Cerberus cannot achieve privacy, and we have some schemes such as PISA, which cannot be supported on blockchains with limited scripting languages such as Bitcoin. Compared with these schemes, our work FPPW can be deployed on Bitcoin, unlike PISA. It can, unlike Cerberus, it can achieve privacy. Like PISA and Cerberus, it can provide alpha fairness with alpha being 1. However, its coverage is higher than the coverage of PISA and Cerberus, and our scheme, unlike Monitor and DCWC, can achieve fairness with respect to the Watchtower. Now I want to tell you how FPPW works, but before that, I want to tell you a little bit about adapter signature, which is used in our scheme. In adapter signature, we have a signer, let's say Bob, whose public key is known to the verifier Alice. Alice assume that generates a statement witness pair using a hard relation. For simplicity, assume that the statement capital Y is a public key of a public key system, and small y or witness is its private key. The statement capital Y is given to the signer, and signer using its own private key generates a pre-signature on message M. Pre-signature is actually a partial or incomplete signature whose correctness can be verified by someone who has access to the public key of the signer, and Alice, who has access to the value of the witness, is able to adopt the pre-signature to a valid signature on message M. And if this signature is revealed to Bob, Bob is also able to extract the value of the witness using the signature, pre-signature, and of course the statement. Life cycle of FPPW consists of 4 phases. The first phase is called channel establishment. In this first, a 2-of-2 multisig address is funded by Alice and Bob with A plus epsilon over 2 and B plus epsilon over 2 respectively. Output of this funding transaction can be spent by commit transactions. The first version of commit transactions is generated and signed by channel parties in the channel establishment phase using the adapter signature. So each party has adapter signature of his or her counterparty on commit transactions. Each commit transaction has 2 outputs. The first output is called the main one, whose value is A plus B and can be spent by corresponding split transaction after small t rounds. Split transaction actually represents state of the payment channel. The second output, which is called the auxiliary output, is used for penalty and revocation purposes, as we'll see. It's and the value epsilon actually is the minimum possible value that can be supported by in Bitcoin network. And as I mentioned, this split transaction cannot be published immediately once the commit transaction is recorded on chain. Its broadcaster must wait for T rounds, and after that, he or she can publish the split transactions. In addition to these transactions, we have a collateral transaction using which the Watchtower logs its collateral in a shared address. The value of the collateral equals the channel capacity. Output of the collateral transaction can be spent by reclaim transaction, and output of the reclaim transaction can be claimed by Watchtower after capital T rounds. We assume that Watchtower is always online, but channel parties gets online almost once per capital T rounds. Capital T is set such that T rounds is equivalent to 1 month, so channel parties must get online almost once per month, which is not a big deal for ordinary users. And small T rounds, which is used in the output of the commit transaction, is around 1 day. Now assume that a channel is in state I and Alice and Bob wants to update it to state I plus 1. To do so, a new version of commit and split transactions are agreed between Alice and Bob. And now clearly state I must be revoked by channel parties. To do so, a revocation transactions are signed by all the channel participants. And something that is important is that the revocation transaction can be immediately published. I mean, once this commit transaction is published on the blockchain, this split transaction can be spent after T rounds, but this revocation transaction can be published immediately, and its output can be claimed by someone who knows witness values of both Alice and Bob. In other words, if this commit transaction is published by Alice, Bob can actually compute the witness value of Alice, and then this output can be claimed by Bob. Additionally, we have two versions of penalty transactions per revoked state, and these penalty transactions also can be published after T rounds. And something that is important is that all these transactions spend the auxiliary output of the commit transaction, so only one of them might be published on the blockchain, and their output can be claimed by someone who knows witness values of both Alice and Bob for this state. To close the channel, channel parties can publish the latest commit transactions, and after T rounds, the latest split transaction. And we know that there isn't any penalty or revocation transactions for this state to be published. And the fourth phase is called channel award, using which the Watchtower can withdraw its service. To do so, the Watchtower publish the reclaim transactions, and after capital T rounds, he will be able to claim its collateral. After that, its service is withdrawn. These were all safe scenarios, but what if one of the channel participants act dishonestly? For instance, assume that one of the channel parties, let's say Alice, is dishonest, so she publishes an old state on the blockchain. We know that Alice must wait for T rounds before being able to publish the corresponding split transactions, but since the Watchtower is always online, he has the chance to publish the revocation transactions, and by doing so, the penalty transactions get invalid, and this output can only be claimed by Bob, because only Bob knows both witness values. But what if the Watchtower is non-responsive? If the Watchtower is non-responsive, the revoked commit transaction can be published by Alice, and Alice will be able to publish the corresponding split transaction after T rounds. However, Bob still has the chance to publish the penalty transaction, and by doing so, all the collateral of the Watchtower is given to Bob, because only Bob can claim this output. But what if the Watchtower has published the reclaim transaction? Then it means that Alice published the revoked commit transaction and a split transaction, and since the output of the collateral transaction has been spent, this version of the penalty transaction is invalid, but Bob still has the chance to publish the second version of the penalty transaction. Something that is important is that this output cannot be claimed by Watchtower for capital T round, since broadcast of the reclaim transaction on chain. However, since the channel parties gets online almost once per capital T rounds. They get online. Actually, Bob gets online before this output being claimed by the Watchtower. So it can be formally proved that FPPW provides a channel party alpha fairness with alpha being 1, whose reason is that the honest channel party doesn't lose any funds in the channel, and collateral of the Watchtower equals the channel capacity. Also, FPPW provides fairness with respect to the Watchtower. Why? Because the reward of the Watchtower is non-zero, because we assume that Watchtower is rewarded after the channel establishment phase and after each time that the channel is updated. And also, using the reclaim transaction, the Watchtower is able to redeem all her collateral at any time. Also, it can be proved that FPPW provides privacy. Why? Because the only transactions that contain some information about distribution of funds among the channel parties is split transaction, and this split transaction is not given to anyone. And this split transaction is only held by channel parties, and value of outputs of all the other transactions contain no information about balance of each party in different channel state. The value of these outputs is fixed per channel. Also, it can be proved that FPPW provides beta coverage with beta being 0.5, whose reason is that the value of the collateral equals the channel capacity, and the value of x over c plus x in that formula is 1 over 2. These are different references that were used in my presentation, and I hope this has been informative for you, and I'd like to thank you for viewing.